Hi everyone, the next topic is variance of beta hat. We estimated the beta in the model y is equal to x beta plus epsilon. So given x and y, the data points that we estimate beta, and the beta hat is given by the x transpose x inverse x transpose y. And this beta hat have some variability. Beta hat is a random variable because when data changes, the beta hat also changes. So here is the example for the two estimation for beta hat. So the first data set is these blue points. And we estimated the line. So y is equal to beta naught plus beta 1 x plus epsilon. And we estimate that line, beta naught hat plus beta 1 hat x. And we observed another data set, the red points. Then we estimated the line. Then we have slightly different line. So the beta hat has some variability. So now we want to estimate the variability of beta hat. In this case, what statistics can explain that variability? We have basically three quantities if we think about second moment. So one is variance of beta naught hat, and another is the variance of beta 1 hat, and the other is covariance of beta naught hat and beta 1 hat. And so we put this in a matrix form, so-called variance covariance matrix, and we want to have the formula for this, the variance of beta hat. So here, the beta naught hat and beta 1 hat, the variance of these are more intuitive, just expresses the variability of beta naught hat and beta 1 hat. Covariance, also this is often not zero. So in this example, the scatter plot, we see the blue line and red line. So these two are typical, the fitted line. And actually, the red line has larger slope. You can see because of, so these two observations, the slope becomes slightly larger than the blue line. But as a result, actually, the intercept is smaller for the red line because most data points are on a positive domain. When x is positive, we observe several observations. So if slope is larger, intercept is naturally gets smaller. So beta 1 hat and beta naught hat have negative correlation. So that makes the covariance negative. So that kind of information is also useful. Okay, so what's the formula for beta hat? The variance of beta hat is given by the sigma square times x prime x inverse. So here, the sigma square is unknown quantity, that is variance of epsilon. So we have to estimate this to get some numbers. So sigma hat square is replaced by 1 over n minus p times residual sum of a square, as we seen in the previous video. And actually, this is also written as 1 over n minus p times epsilon transpose times epsilon, because epsilon is the vector of epsilon 1 to epsilon n. So epsilon transpose epsilon is the summation of epsilon j square. Here, to be exact, this should be epsilon hat transpose and epsilon hat. Okay, so how to prove this theorem? Basically, we use some linear algebra and also property of expectation. So in general, if a random vector E, so that is the random variable, each element is random variable. If the random vector E has expectation 0, then variance matrix of E is expectation of E transposed. So you can see just the, this is from the definition of this variance. So variance covariance matrix of E. If expectation is not 0, it's not centered. So we have slightly more complicated formula. So we have to subtract the square of the expectation of E. But just for simplicity, if we assume 0, then just variance is second moment. Expectation of x squared is equal to variance of x if the expectation is 0. So variance becomes this. Okay, so using this, you can prove the formula for variance of beta hat. So at first, remember that beta hat is equal to x transpose x inverse x transpose y. So that is, okay, so y, okay, so remember that the y is equal to x beta plus epsilon. So you can see this is equal to beta plus x transpose x inverse x epsilon. So x transpose epsilon. Okay, but the obviously beta is constant, so we don't have any variance. So we can just ignore this. The variance is variability, so constant does not matter. So variance of beta hat is variance of x transpose x inverse x transpose epsilon. So by using this property, variance of E is expectation of E transpose, that we can say that this variance becomes expectation of x transpose x inverse x transpose epsilon. This is the same part as this parenthesis. And then we transpose the entire quantity. Then, okay, so in general, for matrix algebra, if we have two matrices and we transpose it, that is B transpose, A transpose. So using this property, we have E transposed first. Then X transpose becomes X, and this inverse becomes this after transpose. So you can prove that the transposed matrix of X prime X inverse is again the same one. Yep, and then we have expectation of epsilon epsilon transpose, and the other terms are all constant. X is constant. X doesn't have any variability. So just this matrix can be put outside of expectation. And here epsilon is IID random variable. So if I and j are different, expectation of epsilon I, epsilon j is equal to 0. And if I, j are the same, just expectation of epsilon I square, so that is variance, so that is sigma square. So expectation of epsilon epsilon transpose is sigma square times this unit matrix, identity matrix. So now this expectation part becomes this. Then this is identity matrix. This should be n in general. Identity matrix. So you can just put this sigma square first, and identity matrix can be ignored. Then further, this x transpose x inverse and x transpose x cancel. So now that we have the sigma square times x transpose x inverse. So this is the proof. Next, R implementation. So at first, we have to define x and y to get variance of beta hat. So in the previous example, that we regressed under count on percentage of people voting for Gore and the percentage of African American, and we need intercept. So we define the x as here, this, and y as this. Then also that we need the sigma hat square, so the SG2, the sigma hat square. We define that this as summation of the squared residuals divided by degrees of freedom. Okay, so now variance of beta hat is calculated by sigma hat square times inverse of transposed x times x. So this is the answer. So this is the variance of beta hat. Okay, so think about the diagonal term. So this corresponds to the variance of each parameter. So for example, the last one is variance of beta 2 transpose. So here beta is equal to beta naught, beta 1, beta 2. So the last term is variance of beta hat. So if we take square root, then that becomes standard error. So standard error of beta 2 hat. And that is 0.03. So this is the variability in the coefficient of percentage of African American. And actually this is given in previous R output, that is summary of linear model. So here you can see the same number here. So estimate was this, but the standard deviation is this. So this is standard error of beta 2 hat. Standard error is standard deviation of some estimated parameter. So we now discussed how to estimate variance of beta hat and its meaning, and also the R code for variance of beta hat.